I'm Tyler Hull,
And I'm Hayden Rich.
and we'll be making a rocket out of everyday household materials.
The materials you'll need are matches, a lighter, some foil, and some paper clips. So the first step, we'll be taking some aluminum foil and wrapping it around the match. You want to get about a nice even rectangle. Doesn't have to be perfect. And what you're going to do is you're going to place the matchstick in the middle of the foil. Secondly, you're going to fold the top half down so that it makes a crease right at the middle of the matchstick. And you're going to want to make sure that the match is held in place tightly by the foil. Next, what you're going to do is you're going to wrap one half around the matchstick and then wrap the rest around that, making sure it's nice and tight the entire time. So the finished product should look a lot like this, where it's wrapped all the way around, nice and tight, and you're ready to go.
So then what you're going to do is you're going to take your paper clip and you're going to turn it into your launch pad. So you're going to bend out the smaller end and kind of widen its stance so it'll stay up and it'll look sort of at a 45-degree angle like that. So once the rocket is positioned on your paperclip launch pad, you want to light the match right under where the wick is, like this.
Wow, what a takeoff! That was crazy. Well, you might be wondering, how did that happen? And I was thinking the same thing. But when we get down to the physics of it, we can start explaining how that rocket really took off. Now, the first two things that come to mind when we think about how this rocket was set into motion is Newton's first and third law. Newton's first law states that every object in a state of uniform motion tends to stay in uniform motion unless acted on by an external force. This is the same for an object at rest. Every object in rest tends to stay at rest unless acted on by an outside force. Newton's third law states that for every action, there is an opposite and equal reaction. Now these both play a part in how this rocket started its momentum or started going forward. The object was at rest initially before we lit the rocket on fire. So in order for that rocket to receive motion, the forces acting down on it needed to be exceeded by the forces acting up on that rocket, thus reinstating Newton's first law. This was done by the chamber we created around the match. When we wrapped the foil around the match and then applied the pressure of the lighter, and allowed a combustion to start taking place, and there was an equal amount of forces pressurizing the rocket on all sides of the chamber. However, there was some space left in the outside of the chamber at the bottom for the forces to be exerted out. That comes into play with Newton's third law. As the forces were thrusting out, the force going downwards had to be equaled by a force going upwards in the same way. Because of that, that allowed the rocket to take off and go forward up into the air. Now, once it reached a certain point, there was no longer a strong enough force to go against what gravity's pulling it down, so it then started going back down to Earth. This is how Newton's first and third laws sort of started taking effect into this situation.
Another important aspect of the match rocket is the conservation of energy, and this means that the energy initially in the experiment is the same as the final energy in the experiment. The energy is the chemical potential energy within the match, means that that is equal to the gravitational potential energy plus the heat. And the gravitational potential energy simply means that the gravitational potential energy is equal to the height of the match times the mass of the match times gravity. And that's how you'll calculate that variable. And then you would add in the heat. And we can actually calculate the heat by saying the mass of the match times the specific heat of the aluminum foil, and then the change in temperature. And so throughout the flight of the rocket, which is this, if it looks something like that, right here, this is when we have all of our chemical potential energy, and our gravitational potential energy will be 0 because we're on the table, the match is still on the table. As soon as the match is lit, we convert all of our chemical potential energy to kinetic energy, and so that's when we have our greatest velocity. And then that energy will transfer to here. This is where our greatest gravitational potential energy is because we have the greatest height. And by the end of the rocket's flight path, when it returns to the table, the energy will be dissipated as heat, which is Q.
Final question remains is how did the components of our experiment actually create movement for the rocket to finally go? That can come into an answer and result is when we finally look at the components of fire. Now, in the components of fire, 3 things are involved: an igniter, fuel, and an oxidizer. The igniter for our specific match was the red phosphorus located at the match head. When we put the lighter next to the match head in our experiment, it allowed the red phosphorus to be brought out and to be heated up, which was what was needed for fire to ignite. Secondly, we need fuel. The fuel is the match itself and and the ingredients located inside the match. Lastly, we need an oxidizer. Now, there's oxygen in the air, which allows for the majority of the oxygen to be consumed and create the fire. But we also needed a bit more, which is created in potassium chlorate located inside the match. This is great. We know how fire is created in our experiment, but does that necessarily lead to movement? Well, let's see. You see, when I light this, nothing really happens besides the fire. So there wasn't necessarily movement yet. Why did our experiment involve movement? Well, you see, when we wrapped the foil around the match, it acted as a chamber. This chamber, since it was foil, allowed to conduct the heat that we used from the Ignite lighter to create more and more heat buildup. The chamber also allowed for the heat to be built up in a certain way, but also there was a hole at the bottom, a tunnel of a sort, to allow for the heat at a certain point to be flushed out. This force, which was used in Newton's laws and also in the conservation of energy, can kind of plays together into letting this experiment receive movement. So as the heat is finally built up to a certain degree, it flows through the tunnel that we've created, allowing for the match and the experiment to take flight. And there you have it, our experiment in a nutshell.
Okay, so the law of conservation of energy can apply to any everyday activity. For example, when I light this candle, the chemical potential energy of the candle was at a certain point, and when I light it, that chemical potential energy is being reduced, but that's being counteracted and balanced by the heat given off by the candle. When I blow out the candle, the heat that was given off and the reduced chemical potential energy would be equivalent, and therefore the initial energy and the final energy would be equal, thus proving the law of conservation of energy.